Hello, welcome to another module of this course, analog circuits. In this module, we will be covering some of the remaining topics on analog nonlinear circuits, namely the clamper circuit, the peak detector circuit, and also what we call super diodes. So, let us go through the circuits. So, let us see the clamper circuit. So, clamper is a circuit which, when an input voltage Vi of this form is given to it, will produce an output like this. Okay. So, basically what it does is remove the negative part of the input. So, the circuit to achieve this operation is given like this. Okay. Now, here what happens is that when Vi is positive, this diode D will be reverse biased and this capacitor will charge all the way to the maximum voltage Vm, and when Vi goes negative, what happens is that the voltage across the capacitance will not change immediately, because that is the property of the capacitor, that it always resists any change to the voltage across its terminals. So, instead the negative voltage that appears across Vi will be transmitted to this diode D, and once this terminal becomes more negative as compared to this terminal, what will happen is this diode will go to the forward biased mode. Once this diode goes to the forward biased mode, this terminal, the volt Vo, will be shorted, and that is the reason we see a short appearing here. Again, when Vi increases or becomes positive, the voltage across Vm, across the capacitor, will continue to be Vm, and the voltage that will appear across the output will also be Vm, because D is now in reverse biased mode and therefore open, and this way the cycle continues. In a practical circuit, of course, we will not find an ideal capacitor. Therefore, in a practical circuit, our circuit will look something like this. There will be a resistor through which the capacitor will discharge. Okay. And because of this, what happens, we will get an output like this. So, this is Vo and this is Vo dash. Now, what happens is the capacitor does charge up to the voltage Vm, but then after that it slowly starts discharging, as a result of which the output voltage decreases gradually. When Vi is negative, then again there is a momentary shift towards the negative region, but then because now the capacitor is again in a charging mode, so what happens is the voltage across the Vo will slowly reach the value 0. Okay. So, this is the cycle that repeats, and because of this discharging and charging, we get these slight distortions in the output waveform. The next topic that I would like to discuss is what is known as a peak rectifier. So, we have already seen rectifier circuits in the last module. These circuits are similar, but they just produce an output that follows the peak of the input voltage. So, let us see what are these. Consider this circuit. Now, in this circuit, suppose my input is a sinusoid like this, okay. So, this is V I and this is T. Now, during the positive half cycle, this diode will be forward biased and the capacitor will simply charge right till its peak value. Say that is, I call that peak value Vm. However, once the input voltage decreases after reaching the peak value, the capacitor will not discharge, because this diode will now be reverse biased, and so the voltage across the capacitor will continue to follow or continue to remain at the value Vm, and it will continue to remain at the value Vm till again the input voltage reaches the value Vm, at which time this will again get short, but once the input voltage starts decreasing from Vm, the capacitor, this diode will again go to reverse bias, and therefore, the voltage across the capacitor will be given by this curve, this red line. Now, because the output voltage is same as the voltage across the capacitor, the output voltage simply follows the peak of the input sinusoidal wave. If in place of a sinusoidal voltage we have some other form of function like a triangular waveform or a square waveform, then also the output voltage will follow the peak value that is given by the input. Now, of course, just like the previous circuit, the capacitor won't be ideal. In reality, what we'll have is, so this is my ideal circuit, okay, and this is my real circuit. Suppose the current flowing through the diode is given by ID, the current flowing through the capacitor is given by IC, and the current flowing through the load is given by IL. So, this load resistance has a value R, say, then my output will be something like this. So, say again, this is, I provide the same input as that for the ideal rectifier. Okay. The voltage across the capacitor, once on reaching the maximum value Vm, will stay there momentarily, okay. But because of this discharging resistance present, the voltage will slowly decline. Okay. So, this is my V0, and then again it will increase when the input voltage exceeds this value, and this way it will continue. So, my output will follow a pattern like this. Okay. What about this load current? If I want to plot the load current as well, then it will be somewhat like this. So, it will follow a pattern like this. Okay. What about the diode current? Suppose if I use a green pen, so this is my IL. This is IL. The diode will be conducting only during this phase, right? Only during this phase. Therefore, during this phase we will find a surge in the diode current like this, okay, and then it will again become 0. So, this is my ID. So, this is how the situation is, and if you can, I leave it as an exercise for you to try to plot IC, which is equal to ID minus IL. Okay. So, I leave it as an exercise for you to find out how the waveform for IC will be. So, in all these circuits we are using, and at least in the last two circuits, that is the clamper and the peak detector, we were using ideal diodes. So, ideal diodes, as I had mentioned earlier, are diodes where the threshold voltage is 0 and also the diode resistance is 0. But in reality, threshold voltage is present in all diodes, and because of that we have seen a number of problems, especially while discussing the half wave and full wave rectifiers. We found that the peaks of the input and output of the rectifiers are separated by the threshold voltage, have a difference, and that difference is given by the threshold voltage. So, wouldn't it be ideal if we could get a diode which would have no threshold voltage? Is it possible? Is it possible to have such a diode which has no threshold voltage? As I mentioned a few seconds ago, that such a diode does not exist. However, we can obtain a circuit using an op amp and a diode which behaves nearly like that of an ideal diode. Such a diode or such a diode based circuit is called a super diode circuit, and we shall be using this circuit for rebuilding our half wave rectifier, and we shall see that the threshold voltage problem does not exist using this super diode circuit. It is called a super diode, as I mentioned, because there is no threshold voltage, or at least the threshold voltage that appears is very negligible. So, this part within this dotted lines is my super diode. R is a load and output voltage is taken across this resistance R. Now, let us see how this circuit operates. First of all, this is say an ideal op amp, and as you know, an ideal op amp will provide infinite gain. So, whenever the input to the non inverting terminal is higher than that of the inverting terminal, I will get an output which should be very high, or for practical op amps it should be equal to the upper saturation voltage of the op amp. So, inevitably, because this diode is connected in this fashion, whatever voltage we present here, whatever positive voltage we present here, this will cause this diode to go to forward bias mode. The threshold voltage will not matter here, because this output VA of the op amp is very high because of the infinite gain, and that will in all cases be greater than the threshold voltage of this diode, and therefore, for even small inputs we will have this diode operating in the forward bias mode with no threshold voltage problem. And so, because for small voltage inputs also this diode goes to the forward bias mode, hence what we will have is that the output will be positive whenever Vi is high or positive. Even for small positive values of Vi, we will get a positive output voltage. Of course, for negative values of Vi, V0 will be 0, because for negative values of Vi, Va will reach the lower saturation voltage, and this diode will be in reverse bias mode. So, if I try to draw the Vi versus Vo curve, it will be something like this. Okay. There will be a slope of 1. So, Vo will directly follow Vi whenever Vi is positive, and Vo will be 0 whenever Vi is negative. Now, there is one small problem with this circuit, which is that Vi appears so the disadvantage of this circuit is that Vi appears directly across the op amp terminal. So, the reason this is a problem is because in all practical op amps there will be some resistance between the input and the op amp terminals, and also since all op amps have some current, though negligible, but still there is some input current. Because of the presence of the small resistance, say if I represent this small resistance like this, there will be a voltage drop at the input, and therefore, Vi needs to be high enough to overcome this voltage drop. But of course, if we consider our ideal circuit, then there is no need to consider this voltage drop, but in all practical circuits there will be some voltage drop appearing at the input. So, to get over this problem, we have another circuit, and the advantage of this circuit is that it operates in the negative values of Vi. So, the circuit super diode circuit that we just saw, it operates only when Vi is positive, or it produces an output only when Vi is positive. What if we want the other case also? So, suppose we need to have a super diode circuit or a circuit which produces an output for negative values of Vi. So, such a circuit is given like this. I leave the analysis of this circuit as an exercise for you, but we should get an input output characteristics which is like this. So, then we already saw the super diode which can be used for a half wave rectifier, the previous circuit, that is this circuit. This will act as a half wave rectifier because of this kind of input output characteristics. If we want to make a full wave rectifier, then we can combine this circuit with this circuit to produce a full wave rectifier. Now, if we just for a moment go back to this second circuit that I mentioned, this also has the advantage that there is an input resistance or a resistance connected to the input, and this acts like a buffer for any small voltage drops that might occur. So, since there is already a resistance present, the input is tuned to any small voltage drop due to any small negligible current that might be flowing into the inverting terminal of this op amp. So, that second problem that we had, that there was a finite voltage drop at the input of the op amp, is removed by this circuit. This is also another advantage of this circuit. So, if we go back to our circuit of a full wave rectifier using both these super diode circuits that we have just discussed, the full wave rectifier circuit, we get it, we can call that a precision full wave rectifier circuit. So, this is just a combination of the two. This is the first circuit that we had discussed, and this is the second circuit we had discussed, and the output and input relationship is given by this graph. Okay. In fact, we can obtain a bridge rectifier, precision bridge rectifier version of the same circuit also, and that is given by So, this is my bridge rectifier circuit. VO is taken by between these 2 points, and I leave it as an exercise to analyze, for you to analyze this circuit and show that indeed the threshold voltage problem will not be here. And finally, we can also find same we can also apply the same technique to the peak rectifier circuit that we had discussed earlier. So, this is the circuit for my peak rectifier, and again I leave it as an assignment for you to analyze this. You will find the peak the threshold voltage problem is not present in this circuit because of the presence of this op amp. Whenever Vi is positive, this diode will always be in forward bias mode even for small values of Vi, and therefore, even for small values of Vi, that is when Vi is lesser than the threshold voltage of this diode, say I call this D1, even when Vi is lesser than the threshold voltage of D1, we will get an output which is proportional to the input. Of course, for Vi being negative, this diode D1 will be in the reverse bias mode, and therefore, the output voltage here will be 0. And the rest of the circuit is simply the repetition of the peak rectifier circuit which we had discussed earlier. So, that brings us to a conclusion to all the topics on analog circuits based on op amps only. we have been covering these circuits for a long time now. We started right in the beginning, in the first few weeks, with the inverting and non-inverting op amps. Then we also saw how to build up filters using op amps, and then finally we moved on to the nonlinear circuits, where we have discussed a number of them, like oscillators, clampers, peak rectifiers, peak full wave rectifiers, bridge rectifiers. In the next module, we shall be moving on to a specific device, the BJT, the bipolar junction transistor, and we shall be analyzing its DC properties, because DC properties of a BJT are very important, especially for circuits which provide voltage at a given value at specific points in the circuit. So, that is why these DC based circuits for BJTs become very important, and we shall be discussing the DC the BJTs used for generating specific voltages, or basically what we call the DC characteristics of a BJT. So, that is what we will cover in the next module. Thank you.